Good afternoon, and thank you for joining us for today's webinar, Get More Out of MongoDB with TokuMX. We are going to start out today's webinar by telling you a little bit about TokuTech. If our performance database engines, TokuMX and TokuDB, both offer high performance and scalability for MySQL, MariaDB, and MongoDB. TokuDB and TokuMX are both open source solutions and are compatible with your existing code and application infrastructure, making them a very easy drop-in solution. Some of the benefits you'll see with TokuDB and TokuMX include improved insertion performance up to 20 times, reduced HDD and flash storage requirements up to 90%, and once again, no need to rewrite any code. On our next slide, you'll see some of our current customers. I would encourage you to visit our site to see how some of our customers, such as Mozilla and Limelight, are currently using TokuTech. Finally, before we get started, I'd like to go over a few quick housekeeping items. First of all, this presentation will be available for replay following the event, both a replay of the full webinar and the slides themselves. We do welcome your questions, but I do want to let you know we won't be answering them until the end of the presentation, but please feel free to ask throughout the presentation. And once again, a copy of the presentation will be available on the website after this webinar. So without further ado, I'd like to welcome Tim Callahan. He's our VP of Engineering, and he'll be explaining how you can get more out of MongoDB with TokuMX.
Thanks, Amanda. With that, we will get started. 1 second. Maybe you just decided to eliminate. Okay. So we went through the housekeeping. Just a brief walk through the agenda before I get started. I have here listed as brief again, a brief Mongo overview, really pointing out some of the interesting aspects of Mongo as I see it, coming from it from the perspective of MySQL. Do a slide or two on what is TokuMX, just to give everybody the same understanding of what the solution actually is and what it's intended to do. Then we'll talk some getting started, easy ways to just get up and running quickly with TokuMX. And then to take the TokuMX story a little deeper, we're going to talk about performance, we're going to talk about compression and transactions. And those are really the three pillars of the TokuMX story: is performance, compression, and transactional support. We'll follow that up with a little bit of a discussion of support itself. You know, what is it like, or how do you support TokuMX in a development, evaluation, and then a production environment? And then at the end, Q&A. So as Amanda said along the way, any questions you have, please type them into the GoToMeeting chat box. We maintain it all in a Google Doc, so I promise not to peek, to get interrupted in the middle of my conversation. But when we get to the end, there should be 5 or 10 minutes to cover questions. Anything we don't cover, we will certainly follow up with an email response. So I thought about putting this in when I decided to rerun this webinar here, and I think it's important to have some perspective. So just to lay the groundwork for the way I see MongoDB and certain aspects of the technology, far and away its primary design goal, I think, was ease of use, and that is really evident when you start getting hands-on with a product like MongoDB. Single binary install. If you skinny it down, there's no shared libraries. You can just get away with the MongoDB binary, and you got to give it a folder, and that's where the storage is going to go. Very few knobs on the server, and sensible defaults for those knobs. So you can get a server running, and it's going to perform, pretty well without doing much tweaking or tuning to configuration files or command line parameters. I think the schema-free nature is very interesting, and again, this really comes from a world of MySQL and some of the limitations there with the technology. So, oftentimes in MySQL deployments, people need to add columns, drop columns, add indexes. All these operations in MongoDB are done without blocking, without downtime. So you want to change your schema, it's just fine. Mongo adapts and handles that right out of the box. I think what this is enabled in the MongoDB world is really rapid prototyping. Try things out, see what works, find out what doesn't. Prototype with as little friction in the development process as possible, which also then becomes, in a production environment, this new theory of continuous deployment. It's very easy to roll out changes without downtime, without maintenance windows, if you want to change something about your schema, add a new column to a very large collection in MongoDB, you just start adding that new field going forward. You don't have to worry about the collection getting rebuilt and having downtimes. These last two pieces I think are really interesting functionality that's very important, and it's great that they put it in the box. First off is what I'm calling better replication, and again I'm comparing and contrasting it to what goes on inside MySQL's replication model. So the fact that Mongo out of the box, it supports automatically promoting when there's a failure. So if you have a replica set, you've got a primary MongoDB server and multiple secondaries, something should happen to that primary. It crashes, it goes down. The secondaries take a vote. Whoever's furthest along in the replication process takes over and everyone else reconnects. There's an automatic promotion process right out of the box, no secondary tools or scripts or utilities. You don't have to make the decision, do I do statement-based replication, do I do row-based replication? And secondaries just don't diverge. So it's a really nice way to, your secondaries are read-only. You can't accidentally sneak in an insert operation. You don't have to worry about comparing secondaries to primaries. Again, given that the time marches on and these systems have to be bigger and more scalable, it shards right in the box sharding. So horizontal scale out is possible without third-party tools, without putting that work in your application layer. So Mongo has understands how to do sharding. It has a special router to handle that, and you can scale horizontally without doing much work. And if you carefully design your applications on the way in, it's a relatively painless process to go from a non-sharded to a sharded environment. So to talk just on one slide, so what is TokuMX and how does it fit into this? One way we like to look at TokuMX is it's MongoDB with improved storage. We've been at this for about seven years at this point, creating something we call a fractal tree index, which is a replacement for a B tree. And we implemented that on TokuDB, and for years now we've been offering and refining that product. We decided to take that same exact indexing technology and put it under MongoDB and make all the code changes necessary to support that index type. And in that process, we removed the existing storage code. So the current way that the oplog is maintained, all that existing Mongo storage technology has been replaced with fractal tree indexes to accomplish what we call TokuMX. And it's a drop-in replacement for MongoDB 2.4 applications. So in our last release, our initial release was 2.2 compatible with Mongo. We backported some 2.4 features. Our goal of TokuMX version 1.3, which was released in December, was full 2.4 compatibility. We've achieved that. Same replication and sharding. It feels exactly the same from that perspective. Data model is the same, JSON, same query language, it's JavaScript. Drivers just work. But important to note, there are a few feature differentiators that exist right now. So there is no full text index support in TokuMX, and there's no geospatial indexing. So if those are requirements of your application, then that particular MongoDB application at the moment would not be compatible with TokuMX and not something you would want to try to port over, because those index types do not exist yet in TokuMX. And we're open source. There's a link to our GitHub repo. All our feature development is being done through GitHub issues. So if you go to the milestone, you can see what we're working on, see all the lines of code, just kind of see where we're taking the product over time. And then we have future feature milestone where we have ideas. And certainly people are welcome to post bugs there, to give feedback on features and ideas we're thinking about working on or are currently working on when we're looking for additional testers. So getting started, I think this is always a daunting process with any new technology, even when the vendor says it's a drop-in replacement. So I looked around the web for an image that kind of made me feel how I felt when I first got into MySQL or started using TokuDB or MongoDB or really any new technology that's different than what you're used to working with. And there's this paper folding technique where you can create what's called a hexaflexagon, and there's a link there if you want to go there. But it's really interesting what the final result is. It feels really complicated along the way, but I think once you do it once, it's really not that complicated. As long as you're following the instructions and someone is there to help you, it's pretty easy to get going. And the reason I draw that out is if we look at what is installation like for TokuMX, as we mentioned, it's a drop-in replacement. If you went to the MongoDB website and the Toku Tech website and you downloaded our tarballs, not package installations, and you untarred them, if you take a look in the bin folder, it's very similar. We still have Mongo, the command line tool. MongoD is the server daemon. The only difference really in the bin folder is this Mongo 2 Toku, which I'll talk about in a few slides. But really, what the slide is intended to get across is it is drop-in replacement. It's compatible. It will look and feel the same to you at a high level. So converting data, you already have a Mongo application and you want to try out TokuMX. There's really two ways to get started. If you've already got Mongo servers running, the everything option is on your MongoDB server. Just run a Mongo dump to a file, take that file over to a TokuMX server where you've installed TokuMX and run Mongo restore. We're compatible with that file. You'll end up with the same databases, the same collections, the same indexes. All the data will get imported, and you're up and running with the same data. The only caveats there are, as I mentioned before, we don't understand, we don't support geospatial indexing, and we don't support full text. So those indexes will not get created because those aren't types we support in our builds. If you just want to get started with a couple collections, it's drop dead easy in Mongo. Again, take your MongoDB server, run a Mongo export on one or more collections, and then take those export files over to your TokuMX server and run a Mongo import. So I find this is a good way to just get hands-on, bring some data over, maybe run some queries, try out some of our different indexing technologies, or look at compression. This is a good way to get started, kind of in an eval, kicking the tires sort of way. On the prior slide, I mentioned this Mongo 2 Toku, which is the one binary that's different and exists in our tarball and not in the Mongo tarball. So what this slide tells you is it's a utility, and the goal there is to enable TokuMX servers to process replication traffic or oplog traffic from a MongoDB master or a MongoDB primary or secondary. And the reason we need this utility is our oplog formats are incompatible. So Mongo's oplog is how MongoDB's oplog is how MongoDB does replication. We utilize an oplog for our replication, but our formats of the objects we're putting in those oplogs are completely incompatible. We're logging messages. Mongo is logging differently inside the oplog. So we built this tool, as that bullet says, it's to enable you to have a TokuMX server coexisting with a MongoDB server. Now that MongoDB server might be a primary or secondaries in a replica set. It could hang off of one or more shards. But again, it's a way to kind of simulate keeping your data fresh in a TokuMX server, keeping it up to date with an existing Mongo server. Now there's effort, right? You can't just start up a TokuMX server and say, get going with this tool, because this tool keeps up with the oplog, but it doesn't necessarily build the server from scratch. It doesn't get all the existing data into the TokuMX server. So what that requires is what I call advanced data conversion here. And this is, normally this can be more about production, but certainly you can be using this in your test and eval environments. And it's a simple three-step process. It's not hard at all. Normally you'd start this, the process from a MongoDB secondary server. So on that server, what you're going to want to do first is disconnect that server from the primary that it's processing oplog from. And the reason being is the second item here. You want to note the position in the oplog where that secondary, how far it's made it through its oplog. And the reason being is we're about to do a Mongo dump in the next step, and I think there's an option within Mongo dump to make it record the oplog position, but we want to know that oplog position. So when we reconnect our TokuMX server, we use that exact same vector to get back into the oplog and to get current with the server itself. So we're going to take a Mongo dump that's going to give us all the data off the server, and then we're going to take that file over to a TokuMX server. I'm calling it a primary here because we probably want to build a replica set off of it eventually. And on that TokuMX server, we're going to run Mongo restore to bring in all our data, build all our indexes, get up and ready. And then the next step there is we're going to run Mongo 2 Toku, that binary, and it needs three parameters. Parameter one is we're going to point it to one or more IP addresses and ports of servers where we're going to be keeping up with the oplog from. The second parameter there is the IP address and port of the TokuMX server we want to keep up to date. And the reason for that is you don't necessarily have to run this on the local host of the MX server. You could have a third server doing this arbitration for you. And the last position is the parameter is the op log position. So we want to tell it, okay, at that specific point in the op log, let's start processing from there forward. The real goal of this tool is for a full switchover in production, because in the switchover process, you'd want as little downtime as possible between shutting down an existing Mongo server or clusters and bringing and coming online with the TokuMX version of that cluster. So the switchover process is easy. If you've followed those first two steps, you have a TokuMX server, and it's keeping up with MongoDB servers. And on that MX server, you could introduce a secondary and make sure you're up and running with replication and ready to go. So your switchover process is really clean. You're going to disconnect your clients from your existing Mongo cluster. Once it's disconnected, at that point, all the replication is going to flow throughout that replica set or the shards. You're going to let Mongo2Toku drain. You want to make sure that everything has drained off those servers. As soon as the draining is complete, you're going to stop the Mongo2Toku process and then reconnect your clients to the TokuMX cluster. So this is a good way. In advance, you can certainly take the backup and get your MX servers up and running and up to date with your primary. What this can lead to is a downtime between switchover that's measured in minutes, or could be measured in seconds if you're really efficient about getting it done. But it's a nice, clean way to migrate from one technology to another in a production environment with as little downtime as possible. So again, it's an excellent way to try out TokuMX as well. So that was about migrating in production, but another example would be, well, it's great to take a Mongo dump from an existing Mongo primary or secondary and put it on a TokuMX server and see the compression and run a couple queries. But it would also be nice to see it staying current and see some workload processing and maybe add some indexes and run some queries. So again, great way to test data compression and see how much your data can compress, because your mileage is going to vary based on the data. Good way to test query performance, to play around with some of our indexing options and see how that affects your queries. I think we've got some really good documentation on this process in the tool, and the link to the website to grab that is in the presentation. So from a memory usage, it's important, if you're going to be evaluating TokuMX and or adopting it, you really want to think about how memory is utilized by both technologies. So MongoDB uses memory mapped files, which means MongoDB is going to attempt to use as much available RAM as possible. And there's a real positive to that. The positive is, without a knob, it's going to use as much memory as you've got. And I think, for a lot of times on ease of use and evaluations, that's a positive. Users aren't going in and detuning by only setting a tiny little amount of RAM for the server to use. The challenge is number one, the operating system gets to determine what stays in the cache. And the operating system has really very little, if any, awareness to what's going on in those memory mapped files. So whether it's going to keep collection data versus indexes in memory, is it going to eject things from that cache based on size? How does it know what's hot and what's important to keep around? Those are all hard questions to answer when you let the OS determine what stays and goes. And again, performance is going to suffer when other memory-hungry apps are on the server. You might be running 2 Mongos on the server. You might be running some Java application servers. It's hard to tune when this process grows for as much as it wants, but other processes have capped memory usage. TokuMX takes a different approach. We've got a fixed cache size. When you start the server, you tell it use 4 gigs, use 8 gigs, use 16 gigs, whatever you want. And that's as large of an amount of memory that we'll use for caching data. What that does for us is it puts us in control. So we decide what stays in the cache when something needs to be evicted to bring new data into the cache. So we might base it on primary versus secondary indexes, internal nodes versus leaf nodes in the trees themselves. There's lots of additional knowledge you can put into the process of ejecting data to bring new data in, and that's really the current problem in the world. Is it's hard to have servers that can contain all the data for your use case in RAM. So I think it allows us to achieve better performance just because we're more involved in the decision process about what to keep around. It also makes it really easy to run several TokuMX instances on a single server without memory contention. So if you want to start up 3 TokuMX servers on a 48 gig server, you can give them each 12 gigs of RAM, and you can know that collectively they will consume 36 gigs and none of them more than the 12 that they have. So it really enables you to have consistent performance and not have one server kind of invading on another's cache and making performance go up and down throughout the day. I/O, MongoDB, as I mentioned, it's using memory mapped files. TokuMX, we support 2 types of I/O here. So we'll support direct I/O and buffered I/O, and there is a trade-off. Different use cases, different evaluations, you might want to make a difference. So I recommend direct I/O, as it says at the bottom. With direct I/O, writes are going straight to the disk. They're not going to an operating system buffer where the operating system is in charge of when it's actually getting written out to disk. What this does is it allows you to declare a larger cache size, gives you better cache hit ratios, and my rule of thumb is 80% of the free RAM in your server is a good place to start with if you're going to have a dedicated server for TokuMX. Buffered I/O is interesting. So the writes in buffered I/O are going to be buffered by the operating system and held there until the OS decides it's time to write. Normally, what you'd want to do here is declare a smaller cache size. By default, we'll consume 50% of cache. But the benefit here is some of the hits are going to come from the OS buffers itself. So this is a good use case where you've written something, it got ejected from the cache, but then you read it again while it's still in the operating system cache. And the last bullet is really where that makes the most sense. If you've got extreme compression in your use case, these OS buffers, instead of containing the cache itself, the TokuMX cache, internally it's going to be uncompressed data, but what goes into the OS buffers is what's being written to disk, which is compressed. So you can fit a whole lot more data into your OS buffers, and for certain use cases, that might be a huge performance boost, especially on reads. Starting the server, as I mentioned earlier, couldn't get any easier. I think Mongo did a great job making this simple and allowing people to get started in a hurry. So to start a MongoDB server that's journaling, which means it's crash safe and can recover, it's merely tell it you run MongoD, where to store your data, that DB path, and a tac journal command at the end tells it to turn on journaling. And therefore, if you had a crash, it could come back to a consistent state. I think the term in the database industry is journal if you care about your data. And there certainly are use cases where people don't, which is fine. Get some better performance if you don't do that. For MX, you can see the command looks very similar. A couple differences. I'm passing tac direct IO to tell it to use direct IO, and I'm declaring my cache size of 12 gig. The last important note here is that with TokuMX, there is no tac journal option. Reason being is there is no way to not journal. I would argue the performance is fantastic as it is, but we are a crash safe storage technology underneath the covers, and we don't have a way to turn off the journaling. So regardless of how you start the server, you will be crash safe and the server will recover in the event of a crash. So I think it's now important to talk about like the merits of TokuMX. So we're talking about getting more out of TokuMX, and I mentioned these pillars: performance, compression, and transactions. Performance is a really interesting thing to talk about. So first off, one of the reasons for a performance advantage here in TokuMX is just the way we do storage and the way we do I/O, how we bring in read data and write data. So in MongoDB at a very high level, Mongo's storing these documents in a heap. And a similarity is if you're a MySQL user, think MyISAM. So MyISAM has a file where it stores all the row data, and then it has a second file where it stores indexes that have pointers. So in MongoDB, these documents are stored in a heap, and then the primary key on that collection and any secondary indexes are stored separate, and they're using B trees. These indexes have pointers to that heap itself. A challenge to that is if something moves in the heap, so say you store a document and it's gotten larger and it doesn't fit where the old document was, it needs to move in that heap. And the challenge of that move is a move requires an index update. So it's hard for people to realize sometimes in MongoDB, if my documents are growing, and there's ways to try to avoid this document movement in Mongo power of 2 sizing or padding are options there. But if you're not doing that, or even those at some point will require moves, just updating a document and not actually changing the primary key or the index could require index maintenance. And as the last bullet here says, that can be really expensive. If you've indexed an array field and there's 100 elements in that array, you're actually going to do 100 index updates. Or if there's a dozen, you're going to do 12 index updates just because your document got larger. In TokuMX, we store, much like we do in TokuDB, just like InnoDB does, we store these documents clustered in the primary key index itself. And then secondary indexes in TokuMX, they contain the primary key. So there's a lookup in the secondary index, which then generates a lookup into the primary key to get the other fields in the document that aren't part of the index. The consequences of that storage technology, in a very general case here is interesting. So just on a simple point lookup, when you're looking something up by primary key in MongoDB, and your use case is greater than RAM, a lot of the things we're going to be talking here is data that can't be constrained, can't fit in main memory. So in MongoDB, you're normally going to do an I/O to look up the primary key, which is going to give you back a pointer into that heap. And then you're going to do a second I/O into the heap to get the document. In TokuMX, because it's clustered, you're just going to do that first I/O into the primary key, and then the document is co-located, so that wouldn't require further I/O to pull it out. Again, very general case, very high level, but these consequences become really apparent as we start to look at some of these use cases coming up. TokuMX also allows you to do something interesting, which is called a clustered secondary index. So the primary key in TokuMX is storing the keys themselves and then the full document right alongside. Secondary indexes are just keys with primary key pointers. But you can optionally, when you create a secondary index in TokuMX, you can cluster it. And what that does is it's going to store an additional copy of the document right in that secondary index. And this is much like a covered index, only it's going to contain all the fields in your document, regardless of schema. And then over time, as you're adding more fields, they will be part of this clustered secondary index as well. So in a covered index, a query doesn't have to actually use anything more than that index to resolve it. Clustered secondary indexes can always do that, regardless of the definition of the key. It's going to save you I/O when you're looking up documents. It's really useful for range scans on the secondary indexes because each of those requires an I/O into the secondary and then a lookup in the primary key. So this can make secondary range queries go substantially faster than they do in an unclustered version and really reduce your I/O requirement. There's downsides. There is a trade-off here. One trade-off is you got to have more storage required because you're making two copies of the document. There's a copy of the document in the primary key and a copy of the document in each clustered secondary index. TokuMX compression to the rescue. When we look at compression here, you'll see why I think that's a trade-off worth taking for some use cases, but it's something worth thinking about. It also means that any updates to the document itself require index maintenance. But again, given the way we do index maintenance, I would argue that's again a trade-off worth taking for some use cases where clustered secondary indexes come in handy. Syntax is really simple. Everything we're doing here with TokuMX, we're trying to keep it comfortable for people who are used to using MongoDB. So when you create an index with TokuMX, that ensure index command is exactly what you're used to seeing. So in this scenario, we pass a clustering :true argument to the ensure index command, and then that index gets built clustering. Keeping in mind here, clustered secondaries, they're most helpful for range scans, but if you're doing point lookups or very small ranges, say 1 or 2 rows, they can be helpful. It depends on how much of your workload is going to that operation. If you have an insert-only collection or where you're not doing much updating at all, that's a great candidate. That removes the argument of that doing any updates on the collection require updating that index. My last thing to challenge people with here is I tend to see one of two things when people evaluate our software and come to me and show me their schema. There tends to be schemas where they use clustered indexes for all secondary indexes or clustered indexes for none. And I think the challenge here is the optimal schema is somewhere in the middle. I rarely see a use case where no clustering is the right end game, nor do I see where clustering everything is correct. So I think it's challenge your indexes, look at them, look at your queries, and then make some decisions or contact us to see if we can give you some advice. Performance relating to concurrency is really important in MongoDB. Originally, Mongo implemented a global write lock, which meant there was one writer at a time in the entire MongoDB server, and everybody else waited, and when that writer finished, the next one went. In MongoDB 2.2, this lock got moved down to the database level. So now you have, in MongoDB, you've got concurrency at the database level, which unfortunately can cause people to make design decisions which might not be optimal. Some people will start putting collections and spreading them across databases to try to remove this concurrent writer situation. It definitely can severely limit the write performance of a server. Your server might be largely idle because of this one writer restriction, or you might try to architect something to get around it. As I said, spreading your collections around databases, or if you want to keep them all in a database, I've seen write-ups where people put an extreme high number of shards on a single server, and it can certainly get you more concurrency. It's going to spike your operational complexity, what you're managing. Googling around will give you some information and advice. People, there are ways to implement this and get better concurrency that are ideal and optimal and work better than others. So I encourage people, if you are hitting this wall with concurrency and staying with Mongo, there's some good advice on the web, as well as some people who've found challenges in implementing. The difference here is TokuMX. We implement locks at the document level, and this provides extreme concurrency. If you look at this stack here, in Mongo 2.0 and prior, there was a lock at the instance level. In Mongo 2.2, it's been brought down to the database level. Within databases, you have collections in MongoDB, and then within collections, you have documents. And at that document level is where we have our locking applied in TokuMX. And what that means to performance is interesting. I've got a couple experiments that I've run here and benchmarks, and I'll give some explanation and some color to them. So running an in-memory test here, just to show how important concurrency is. If we take this sysbench workload here, so here we're defining a transaction. Just consider that an envelope that consists of an amount of work. So a sysbench transaction is a few point queries, a few range queries. In SQL, it's a sum. So in Mongo, there's an aggregation query that gets run. It does a couple updates. It then deletes a row and inserts the same row with new values. So the workload never gets any larger, but you can just run it and run it and run it. And what I find interesting is, and I think this is true, if you keep your working set in memory, then Mongo tends to perform well. So taking that to heart, I designed this benchmark to say, okay, let me run with a workload that easily fits in main memory. So I think the working set, or the entire data set for this use case, is about 4 gigabytes. I'm running it on a server with 48 gigs of RAM. When I run it with TokuMX, I'm using a cache of 12 gigs. So for both technologies, completely fits this workload in RAM. And as you can see, it's the concurrency bottleneck on Mongo that's hitting it early. So going from 1 to 2 to 4 to 8, I am getting some climb in transactional throughput, but then it's actually working against itself. But it's peaking at about 500 transactions per second, whereas TokuMX is scaling quite nice up to about 16 concurrent connections. And this is being run on a server that's got 2 sockets, 4 hardware threads plus hyper-threading per socket. So these scaling numbers make sense to me, but it's certainly our goal at Tokutech to keep improving the scaling of the product. But this is a fully in-memory workload. If we take it to out of memory, this is where it really starts to get interesting, because in an environment like MongoDB, where there's only one writer at a time, if you're forced to go to disk to get data, it's a real challenge. So in this one, you can see that it doesn't scale much. 8 threads is probably peak. I think this entire workload got up to about 20 transactions per second, whereas at 128 clients, TokuMX scaled up to about 200 transactions per second. And this is all about the write lock getting in the way, and I/O having to occur and slowing things down. And then the last interesting use case that I see is what we'll call indexed insertion. So most of the users who come to us and are evaluating TokuMX or deploying it, this is normally a big part of their workload. You've got X thousands of things per second to get into your database, your MongoDB server, and it's a challenge without sharding, especially to be absorbing something at the rate of 1,000 inserts per second or 2,000 inserts per second on MongoDB, just because of this problem. Your data gets large, it no longer fits in memory, and you're forced to do I/O, and you'll end up with a relationship where you can probably do as many inserts per second, give or take, as the number of IOPS that your disk subsystem can provide. And you're going to have to do a little math there to account for secondary indexes, because those require I/O as well. Whereas with TokuMX, the line kind of stabilized at around 10,000 inserts per second for this use case, and we took it out to 100 million inserts. So this use case at about 30 million inserts was significantly larger than RAM, and TokuMX just kept on going at that high level of performance. Your application, it's a good question. How fast will you go? We encourage people to evaluate, try it, and give us feedback. Two other points on performance, replication, and sharding. So, as I mentioned before, Mongo did a great job of including replication out of the box, and they made some improvements on the MySQL model, in my opinion. And the goal here is to provide read scaling to your secondaries. So you bring up a primary with a pair of secondaries or just a single secondary. The secondary is serving two purposes. It's as writes go to the primary, they're getting sent to the secondary, and it's there for high availability. It's going to have automatic failover should the primary die. It's going to let you add and remove servers without downtime. You can kind of do a rolling upgrade if you needed to. What's interesting and important to me is this read scaling. So if you have a part of your workload is read-only and your secondaries are keeping up with the master, then a read-only query doesn't have to be sent to the primary, to the master. It can be sent to the secondaries, and then you're not putting more load on your primary, which allows you to do more writes there. The challenge I see with MongoDB replication is that secondary servers have to do as much as the master does with respect to writes. So it's kind of an interesting challenge. When inserts, updates, and deletes occur on the master, on the primary, they get sent to the secondary. The secondary does just as much work as the primary did to get that new document in. So if it's doing an insert, it's doing uniqueness checking, for example. And this really can limit the amount of how much of that secondary is available for read scaling, because if your primary is sized for your write workload and you want to offload reads to your secondaries, and those secondaries are doing almost as much write work as the primary, you're really not gaining much in that secondary with respect to reads. In TokuMX, we rewrote replication, and we took advantage of some aspects of fractal trees that's not available in a B tree. Specifically, we're going to leverage the message-based infrastructure. So inserts are just message injection. They don't require I/O. And what we're able to do here is bypass some of the hard work that was done on the primary. So on the primary, if you did an insert and there was a uniqueness check and it passed, then we know it passed. We do not need to do that uniqueness check on the secondary. Or if you're doing an update on the primary, or a delete, for example, that's index maintenance. And we have to find out what the before image of the row was, and now we know what the after image is. That before lookup was done by the primary. We put that in the omp log. We can apply that to the secondary without doing the lookup, and again, just message injection. So nearly 100% of the capabilities of that secondary are going to be available for read scaling, and very little of that secondary's capacity, very little I/O, very little CPU is going to go toward keeping up with the primary itself. It's going to be less lag, and it's going to be more available for reads. Sharding, again here, Mongo did a great job of including support for this. Really good for horizontal scaling, something to keep in mind as you're building your MongoDB application. As I said here, many use cases can go faster with sharded clusters. There's a big however here. There are issues or performance implications of sharding, and one is going to be migration. As data grows on one server, Mongo wants to keep things balanced. There's a balancer. So if too much data is going into one server, eventually it's going to want to migrate some of that data to another server, and that's going to be disruptive. That's going to require queries on the source, on the shard that got too big, It's going to require deleting, looking up data and deleting it from that server, and then moving it across the wire and inserting it to another server. And again, each shard is only as performant as MongoDB allows. So it is going to be disruptive on your workload. Our sharding, in my mind, improves upon this. Take something that already worked very well at horizontally scaling, but we offer clustered indexes, as I said prior. So we cluster the shard key, and that's going to really improve the range scan performance, which is required for migration. Require a lot less I/O, and really make those deletes and inserts, deletes from the source server and inserts on the server where we're migrating to, are going to be much more efficient. And again, our better per server performance is going to keep this running nicely and nice and smooth. So topic 2 here is compression, and then the last piece is transactions. It goes without saying, you can fill out any database name in here. So MongoDB needs, as disk space needs. Mongo databases, I think, often grow quite large for a few reasons. One is it's really easy to get started and store large documents and just start throwing data into MongoDB without maybe really thinking about your problem and what the schema should look like. I think because of that, people tend to keep these documents around for a long time, thinking there might be value in pulling the data out later. It also gets large because in a schemaless environment like Mongo without joins, you're often denormalizing your data. So there's a lot of redundancy, a lot of data that's going to appear several times in documents because unlike an SQL schema, you're not going to have a table with lookups. And this creates operational challenges. Huge disks, 4 terabyte SATA disks, they're cheap, but they're not fast. Cloud storage tends to be even slower, generally. Fast disks, and we'll call these flash and SSD devices, they're really fast and they're really expensive per gigabyte, especially compared to spinning disks. No matter what you do, backups are large as well. Your backups are going to be as large as your source. Unfortunately, at this time, MongoDB doesn't offer any compression at all. So users are faced with, if you want to compress your data, you're going to compress it in your application. You're going to put it into MongoDB in compressed form. You're going to need to decompress it on your own when you get it back. And that data, from a Mongo perspective, is not going to be very usable. You wouldn't be able to query on compressed data, for example. TokuMX needs less disk space by design. We offer built-in compression. Even without compression, I think we're a little more efficient in terms of space utilization. We've been doing storage and retrieval for quite some time, and that's all baked into the fractal tree technology that supports TokuMX. We support 4 compression algorithms today. QuickLZ is fast and light. zlib is in the middle. LZMA is the slowest but the best compressor. And then we have a none option. In our labs, we've got builds on GitHub right now. We're testing out Snappy, LZ4, and LZ4HC. So we've got a very pluggable compression architecture. It's really easy for us. If a new compression algorithm comes out that has merit, we'll test it. If we find value, we'll include it. And it's very, very easy to add new compression algorithms to TokuMX at any time. And the last bullet here is important. Everything gets compressed in MongoDB in TokuMX when we store it. So field names and values. So unlike a SQL database where you have schema and structure and you're only storing and retrieving the values within the columns, in MongoDB, the document itself gets stored, its JSON gets converted to BSON, but the field names are in there in the data to be compressed, which is one reason people tend to keep field names slim. And we compress secondary indexes as well as primary keys. So to show a quick test on the kind of compression you can achieve, I used a data set down bottom. You can see where you could grab it yourself if you want more information. But this is someone from Brown named Andy Pavlo. He created a couple public data sets that are interesting and fun to look at. So this is a data set of BitTorrent peer snapshot data. So there's 31 million documents in here. It's got 3 indexes on the collection: peer ID plus created, torrent snapshot ID plus created, and created alone. The ID is the primary key for the table. And I loaded that into MongoDB. I also loaded it into TokuMX using our 4 compression algorithms. So loading this into MongoDB, it was just over 20 gigabytes on disk in Mongo. In TokuMX uncompressed, it was just under 15 gigs, 14.6. And then you can see QuickLZ, zlib, and LZMA. As I said before, LZ is the lightest compressor. So that went down to 2.25. 1.75 for zlib, and 1.33 for LZMA. What does that mean in general? I recommend people use our default compression. So for this particular data set, using zlib compression, TokuMX achieved 11.6, so just under 12 to 1 compression on this data set. And that means I went into the file system in the DB path for MongoDB and for TokuMX. I did a du command, and I reported exactly how much file system space was being taken up for this. It's also interesting to note, as I mentioned before, we've been at this for quite some time. We do our best to eliminate fragmentation within our files themselves. So, there's an interesting difference in disk space views just for uncompressed within TokuMX. And uncompressed for us is truly that. We are not applying any compression to the data itself. So for a quick comparison here, LZMA, the speed is low, it's slow, but the compression achieved is phenomenal. zlib is in the middle of the road. Compression achieved not that much worse than LZMA, but measurable. And then you can see the examples there for quick LZ and none. What's interesting here is to think about compression in another way. So one aspect of compression is to save space on disk. The other reason to do it is to save I/O. And it's interesting here, if you look at what I try to represent up top is time, and how much of the time goes to the various processes. So if I need to get some data off of a spinning disk, you measure the speed of a disk fetching something in milliseconds. And we often measure decompression in microseconds. So really, the time there to get something off disk is dwarfed by the I/O, the cost of I/O. Meaning, something like LZMA might be interesting if it can save me an I/O, because if I take 50 microseconds to decompress something with LZMA, but 5 milliseconds to fetch it, it's a huge win to save an I/O. When I take that to flash, SSDs and flash, PCI devices, it becomes a different game there, because flash I/Os can be measured in microseconds, and decompression can suddenly get in the way. So that's an example where zlib or quick LZ might be a better choice, because your I/O is very inexpensive, and you want to go faster. But as you can see, time is shrunk because the I/O cost itself has gotten smaller. So it's interesting, regardless of your RAID system, your storage type. If you're evaluating TokuMX, try the different storage techniques, measure how much it's actually compressing, and then run your workload and see what it does to your insertion performance, to your queries themselves. The last piece here is transactions. So MongoDB doesn't support what we would call in the SQL world multi-statement transactions. So each operation you're doing in Mongo is visible to everyone. There's workarounds, you can Google about it, and certainly people have implemented ways to avoid some of the lack of transactional capability, or it's a different mindset. You build your solution such that it doesn't need these types of transactions. Mongo also doesn't support multi-version concurrency control, which affects your queries, and we'll talk about that in a moment. But what it means is readers don't get a consistent view of the data. So you run a query in Mongo, especially big queries. Those queries, as they're running, will eventually get blocked by writers. They'll get their work done. The reader gets back to work. So you might not see a document that should have been there based on when your query started. You might see a document twice because it's been updated and moved further down, and you read it twice. There's patterns and ways to work around this, but I find it a challenge to put on the application developer, and I think it's compelling to have it in the storage stack. So in TokuMX, we offer ACID multi-statement transactions. We're doing locking at the document level. No changes are going to be visible to anyone else until you commit. You can roll back. Crash recovery is only going to recover committed transactions. And also important to note here, so this multi-statement transactional behavior, I apologize for not having it in the slide, it's not available in sharded environments. So this is a feature that's only works on standalone servers and replica sets currently in TokuMX. MVCC is interesting in my mind because you get read consistency. So you start a query in TokuMX. If it takes a microsecond, a second, a minute, an hour, regardless, you're going to get a read consistent view of the data as of when your query began. So creating additional complexity in your schema, finding workarounds for this behavior, or maybe it's unimportant. In any event, it just works. and it's a behavior of the server as opposed to trying to bake that behavior into your schema or your client applications. Transactional syntax, very, very simple. Create a connection to Mongo, run a begin transaction command. You need to stay on that same connection, so if you're connection pooling, you need to use a driver that supports staying on a single connection, because if you jumped connections, you would suddenly be out of that transaction. So in this example, I'm going to insert George, Larry, and Frank into a collection called foo, and I'm going to run command commit transaction. So until I issued commit transaction, no one else connected to that server can see George, Larry, and Frank. If another connection went in and tried to insert Larry, it would wait because I have a lock on that document. I commit the transaction, everybody sees it. If I did rollback instead of commit, all that data would be removed as if the inserts had never occurred. I think there's some really good blogs that we've written so far, and there's more to come that talk in more detail about transactions. And I think we have a webinar either next month or in March that go really, really deep into the transactional behaviors and semantics of TokuMX. Last up here is support. We offer TokuMX in 2 editions. So the community edition has community support, as you'd expect. We have a Google group called TokuMX User. Most of our support team here and engineers lurk on there and try to do our best, same day or soon thereafter, to be responding to people. It's nice to see community starting to support itself in there. Then we have an enterprise subscription, and that subscription is going to get you commercial support. And an item there is, you'd probably rather, after you built your TokuMX application and deployed it, move on to the next application instead of trying to do the technical support for the application itself, for the technology stack. The enterprise subscription also gets you extra features. We currently have a hot backup tool that's part of our enterprise edition that enables you to back up a live running server without downtime. It's going to get you access to the experts. You're going to have a more direct line of communication. You're not going to be coming through a Google group or a generic email. You're going to go right into the ticket system for resolution or ideas and working with us to improve your usage of the product. And then, I think the other thing that's interesting, you get a little more input to the product roadmap. We've got ideas. We've got features coming. You get a little more weight in terms of voting on what's coming when you're subscribed to a commercial subscription. So that is it. This is the final slide. Certainly, we encourage people to come in and download TokuMX at the URL shown there. Register on the site. You get updates, easy access to premium content, and invitations to future events. We've got presence. We've got an RSS read, but we've got Twitter, LinkedIn, Facebook. We got a YouTube channel with some videos coming soon, and a Google Plus account. So at this point, I see some questions have come in, so I will move over to the Q&A and start answering. First up, first question. As I've read about TokuMX, it doesn't come with MongoDB by default. It's a wrapper on the top of the MongoDB. Am I right? Is TokuMX a freeware DB? So, so TokuMX is a full distribution. It's drop-in replacement. So you come to our site, you download the community edition or the enterprise edition, and what we give you currently is a tarball. So it's as if you went to MongoDB and got their tarball distribution. Same thing, you would untar it, and that's going to have the binaries MongoD, Mongo, MongoS, fully standalone, everything you need. It's not, you don't take MongoDB and add TokuMX to it. It stands alone. It is its own thing. We don't currently have packages and package management. It's something we are working on, but if you come get it as a tarball, that's the way it's packaged. And from a freeware perspective, yes, there is a community edition and a enterprise edition that requires a subscription. Next question, what was meant by downtime for column changes? So what I was referring to there was just in the world of MySQL. In MySQL, if you, on an NODB table, if you want to drop a column, add a column, expand, make a column wider, there's downtime. So the table gets rebuilt, and while the table is getting rebuilt, it's read-only. There's some third-party tools, and MySQL 5.6 has built in some functionality to help that be an online operation, but there's an expensive cost to the performance of the server for that to happen. So that's what I meant. And in MongoDB, it's a schemaless design. So if you want to add a column, what it means is going forward, you're just putting a new column in the collection going forward, but it doesn't have to actually backport those column changes to existing documents. There's a question that has specifics I don't know the answer to, so we'll get you that. It's about removing a 2.4 bug present in MongoDB, about a failure with arbiters to replicate, so we'll get you that answer. Is TokuMX a new storage structure? I would say no. So TokuMX, as I mentioned before, it's MongoDB with different storage. The storage underneath it is our fractal tree indexes. So we have a standalone fractal tree shared library that we've used for years to create our storage engine for MySQL. That same exact technology is being used for TokuMX. So the footprint on disk, those are all the files you see are fractal tree indexes. They know how to recover, they know how to compress, they know how to do checkpointing, and they know how to do queries and CRUD operations. So it's existing technology that we've repurposed for TokuMX. And again, we've argued that fractal trees are a drop-in replacement for B trees. Down the road, I think it's a safe bet that we will continue to implement under other database technologies. If we find a database that looks compelling and has a structure with which we can implement fractal tree indexes, we will replace the B trees. Next question, is the TokuMX oplog idempotent like the MongoDB oplog is? The answer is no. Our oplog is fractal tree messages, so they are not idempotent, cannot be reimplied. Would Mongo to Toku work between a Mongo sharded cluster and a Toku sharded cluster just using MongoS Toku routers as the source and destination? I do not believe so. So, the example I used for Mongo to Toku was really about migrating a replica set. When you introduce sharding, it is trickier. We're working with users on ways to make that as easy and convenient as possible, but it is tricky because you also have the challenge of the load balancer, of config servers, and getting a point-in-time snapshot is a challenge. So it's something we're looking to improve over time, but it's certainly, at this point, a work in progress. Next question, can secondaries in TokuMX be hidden as in MongoDB? Do these secondaries support retagging? I don't understand the retagging question. I'll look up the answer to that, but they can certainly be hidden just as they are in MongoDB. Next question, does MMS work well with TokuMX? Stats, backup, etc. Stats, yes. Backup, no. So the MongoDB MMS backup service is feeding off of the MongoDB oplog. So if you try to enable that with TokuMX, it would not work. You can certainly, and we've had people do this, you can connect a TokuMX server to MMS. It will work. There are some interesting behaviors you'll see, just like if you ran MongoStat. So for example, an important stat to know that your data, your working set fits in RAM is a low number, if any, page faults. We don't have page faults. So you will never see that column non-zero in MMS monitoring or in MongoStat. But you can hook the two up. You can hook up TokuMX to MMS monitoring, and it will work just fine. Next question, is the aggregation framework completely compatible? Faster, I'm hoping or assuming. Compatible, yes. Faster, that's going to be dependent on your indexing. If you can take advantage of richer indexes, if your server has more capability because it's not working so hard for inserts, or if you clustered secondary indexes, certainly we could make some of those aggregation queries faster. Do we have a plan for implementing MVCC for sharded environments? So MVCC and sharded environments will work. It's just multi-statement transactions that won't. So if you're sharded, the MongoS router will send the query to any involved shards, and the result sets you'll get back will be MVCC as of the point in time that the particular query hit each server. So there might be a slight skew in that it might not begin that query at exactly the same point in time, but the read itself will be MVCC. Do we have a monitoring solution? That's a work in progress. We've got some interesting things I hope to announce soon about monitoring. Is there support for transactions in the drivers? Currently, it's a challenge because given that MongoDB doesn't support multi-statement transactions, there's not a lot of appetite in the driver maintainers to support it. So I do all my benchmarking and my test applications in Java. Um, you can run command begin transaction, and you can tell the Java driver that I want a particular thread to stay on a single connection for the life of the implementation. So there, I would say there's some support, but it's, for example, run commands are not quite as native as we would like them to be. So you can make it work, but it's not native to the drivers at the moment. Does Toku need compaction every now and again if there are a lot of deletes or when a sharded cluster and chunks are moved around? Not in the MongoDB sense. I think Mongo has a reindex command that rebuilds and does a level of compaction. You can certainly end up with scenarios where if you've deleted a lot of data, there's some space reclamation to be done, and we have an optimized command like we did in MySQL. So that is one way to get a fractal tree index. It doesn't rebuild it, it's actually doing compaction, pushing messages down and cleaning up as things hit the bottom. But our goal is for that to be as non-needed as possible. And we keep getting better with it with each release. I'll answer one more question. We're about 4 minutes past the hour, but this one looks interesting. It says, after a customer starts using TokuMX, what do they normally start complaining about when the excitement of much better performance has faded? Is it speed, disk speed, or what is normally their next performance ceiling they hit? That's an interesting question. So I think what we're finding is people are broadening what they're doing in their application. So if they had a disk constraint and suddenly they've got plenty more disk space available, maybe they're retaining more data, and instead of keeping 3 months of data, they're keeping 6 months, which might change how their users, the business case for the application. They might be adding more indexes which let them satisfy queries they couldn't satisfy before, or they might just be collapsing their infrastructure. They might be happy, they've freed up a bunch of servers or a bunch of server licenses, and they can now save money in terms of redeploying or building new future applications going forward. I think it's an interesting iterative process as you get comfortable with some of the technology. At some point, the process of selecting clustered indexes clicks, and you start to look at your use cases, and you can easily weed out which should be clustered and which shouldn't, and moving it there. But I think we tend to see the fade is more that they figured out what they need to do with that application. It's up and running on TokuMX, and then they're just seeking out new applications to build. So that is it. With that, I'll end the webinar. There's a couple questions I skipped for various reasons. Either I need to do a little bit of research, or the answer would be so complex it's just better that I type it. So we will get back to everybody on these questions probably by end of day today. I appreciate everybody coming, and Amanda, thanks for getting this started.